Hey there, future doctors. We're about to embark on an exciting journey into the heart of chemistry, the first law of thermodynamics. Don't worry, it's not as scary as it sounds. Think of it as the law that governs energy, the driving force of the universe. It's like the law of gravity, but for energy. Just like you can't create or destroy matter, you can't create or destroy energy, only transform it from one form to another. That's the essence of the first law of thermodynamics, and it's a fundamental principle in chemistry, physics, and even biology. In this crash course, we'll demystify the first law and explore its implications for chemical reactions. We'll dive into concepts like work, heat, internal energy, and enthalpy. We'll also conquer Hess's law, a powerful tool for calculating energy changes in reactions. Get ready to ace those NEET questions and unlock the secrets of energy transformations. Let's get started. Before we dive into the first law, let's talk about work. In our everyday lives, work usually means something we do, like studying for exams or playing sports. But in thermodynamics, work has a very specific meaning. In thermodynamics, work is all about applying a force to move an object over a distance. Think about lifting a heavy weight. You apply a force upwards, and the weight moves a certain distance. That's work. Now, you might be wondering how this relates to chemistry. Well, imagine a gas expanding inside a container. The gas molecules are like tiny weightlifters, pushing against the walls of the container and causing it to expand. That's work too. The key takeaway here is that work involves a change in the volume of a system. When a gas expands, it's doing work on the surroundings. When it's compressed, work is being done on the gas. Now, let's talk about heat, another crucial player in the world of thermodynamics. Heat is energy that flows from a hotter object to a colder object. Think about what happens when you touch a hot cup of coffee. Heat flows from the hot coffee to your cooler hand, making you feel warm. In chemistry, we often talk about heat being absorbed or released during chemical reactions. For example, when you burn wood, heat is released into the surroundings, making the fire feel hot. This is an example of an exothermic reaction. On the other hand, some reactions require heat to occur. For example, cooking an egg requires heat to be absorbed from the pan. This is an example of an endothermic reaction. The key takeaway here is that heat is the transfer of thermal energy between objects or systems at different temperatures. Now, let's dive into the concept of internal energy. Every system, whether it's a cup of coffee, a balloon full of gas, or even you, has a certain amount of energy stored within it. This stored energy is called internal energy, and it's the sum of all the kinetic and potential energies of all the particles in the system. The kinetic energy part is all about the movement of the particles. The faster the particles move, the higher the kinetic energy, and the higher the internal energy of the system. The potential energy part is all about the interactions between the particles. These interactions could be due to intermolecular forces or even chemical bonds. Here's the catch. We can't actually measure the total internal energy of a system directly. It's like trying to count all the grains of sand on a beach. But don't worry, we can still talk about changes in internal energy, which is what really matters in chemistry. Section 5. The first law. Putting it all together. We've covered work, heat, and internal energy. Now, let's bring it all together with the first law of thermodynamics. Energy cannot be created or destroyed, only transformed. The total energy of the universe remains constant. It's like a giant energy bank account. Mathematically, du equals Q plus W. du is the change in internal energy. Q is heat and W is work. The change in internal energy is the heat added plus the work done. Section 6. Enthalpy. A new energy hero emerges. Now let's talk about enthalpy, a thermodynamic property that's particularly useful when we're dealing with constant pressure conditions, which is often the case in chemical reactions. Enthalpy, H, is defined as H equals U plus PV, where H is enthalpy, U is internal energy, P is pressure, and V is volume. At constant pressure, the change in enthalpy, dH, is equal to the heat exchanged between the system and its surroundings. dH equals Q at constant pressure. This makes enthalpy a very convenient property to work with because we often measure heat changes in the lab. Section 7. Heat capacity, storing up the heat. Have you ever noticed that some objects heat up faster than others? For example, a metal spoon heats up much faster than a wooden spoon when you leave them in a hot cup of tea. This difference in how easily objects heat up is due to a property called heat capacity. Heat capacity, or C, is the amount of heat required to raise the temperature of a substance by 1 degree Celsius, or 1 Kelvin. The formula is C equals Q divided by delta T, where C is the heat capacity, Q is the heat absorbed or released, and delta T is the change in temperature. Different substances have different heat capacities. Water, for example, has a relatively high heat capacity, which means it takes a lot of heat to raise its temperature. This is why it takes a while to boil water. Metals, on the other hand, have lower heat capacities, which means they heat up quickly. We can also define molar heat capacity, or cm, which is the heat capacity per mole of a substance. This allows us to compare the heat capacities of different substances on a mole-to-mole basis. Section 8. Hess's Law, the energy shortcut. Now, let's talk about Hess's Law, a powerful tool that allows us to calculate enthalpy changes for reactions even if we don't have all the experimental data. Hess's law states that the total enthalpy change for a reaction is the same whether the reaction takes place in one step or a series of steps. This is because enthalpy is a state function, which means its value only depends on the initial and final states of the system, not on the path taken to get there. Hess's law is incredibly useful because it allows us to calculate enthalpy changes for reactions that are difficult or impossible to carry out directly in the lab. We can use known enthalpy changes for other reactions to figure out the enthalpy change for the reaction we're interested in. Section 9. Enthalpy. Changes in reactions. A whole new set of energy transformations. Now that we've covered the basics of enthalpy, let's explore some specific types of enthalpy changes associated with chemical reactions. Enthalpy of bond dissociation. The energy required to break 1 mole of a specific type of bond in a gaseous molecule. Enthalpy of combustion. The heat released when 1 mole of a substance is completely burned in oxygen. Enthalpy of formation. The enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. Enthalpy of atomization. The enthalpy change when 1 mole of a substance is converted into gaseous atoms. Enthalpy of sublimation. The enthalpy change when 1 mole of a solid substance changes directly into a gas. Enthalpy of phase transition. The enthalpy change associated with a change in the physical state of a substance, for example, melting or boiling. Enthalpy of hydration. The enthalpy change when 1 mole of gaseous ions dissolves in water to form hydrated ions. Enthalpy of ionization. The enthalpy change when 1 mole of a gaseous atom or ion loses an electron. Enthalpy of solution. The enthalpy change when 1 mole of a substance dissolves in a solvent. Understanding these different types of enthalpy changes is crucial for analyzing energy transformations in chemical reactions. Section 10. Conclusion. You've mastered the first law. Congratulations! You've journeyed through the exciting world of the first law of thermodynamics. You've learned about work, heat, internal energy, and enthalpy. You've even conquered Hess's law. Remember, the first law of thermodynamics is a fundamental principle that governs energy transformations in the universe. By understanding this law, you've gained a deeper understanding of how energy drives chemical reactions and processes. Now that you've mastered the first law, you're well on your way to acing those NEET exams and achieving your dreams of becoming a doctor. Keep those energy levels high and keep exploring the fascinating world of chemistry.